Are you designing a high-pressure aeroponics system, but you're not quite sure if you're doing it right? With this tool, you will get it right. Welcome to the High-Tech Gardener. My name is Lee Massey. I want to take this time to thank some of my subscribers. You have reached out and left beautiful comments. Here are some of those who have left comments. Hey Rick, Andy, Justin, Thousand Nations, Cad with the K. I want to reach out and thank all of you guys. And I hope to continue to give you information that will help you to build your high pressure aeroponic system so that I can take your garden into the future. As you can tell, today we are out of the laboratory. I'm out actually on a business trip. So I thought this would be a prime opportunity to give you an update of the aeroponics calculator. As you know, I am a software engineer and I like to tinker with code. That's the way that we think. So I have actually redesigned the interface of the calculator 3 times. And the reason why is that I'm trying to make the calculator more responsive. What do I mean? I mean that when you change the values in one field, the other fields will update automatically. You don't have to hit a submit button. You don't have to hit the enter button. It happens instantaneously. It will ripple through the whole program. So if you change your misting nozzles, you will see the values updating in real time, so you can actually see what's happening by changing different values. Maybe later on we will have the report give you a graphical interface so that you can visualize what the changes will do to your system. Now let me talk a little bit about the amount of time that I have spent on this so far. I've been working on this, as you know, for a little over a month. And so I'm doing this part-time. So today, up to today, I have spent close to 39 hours in the development of the aeroponics calculator. But this will actually go up higher. I'm assuming it probably maybe 4 times more, would be my guess, when this is all said and done. But what I have come to notice and come to appreciate is that as I am building out this calculator, not only does the calculator give you values and some guidelines on what you should do, but it's also putting my design in a digital format. What do I mean? Well, there are some decision factors that need to be considered in the calculator. For instance, when you design your system and you know that your pump uses so much power, how do you translate that into the amount of backup power you should have? Should you have twice as much as what the pump uses? 3 times? 10 times? So those values are arbitrary, meaning that it's up to you to decide, how far you want to carry out your design. How much reliability do you want to have built into the system? How much redundancy do you want to have into the system? So these values, you can say, are arbitrary up to the designer. So my calculator is going to be a reflection of me, of how I design my system. So the calculator, don't take it as a hard, fast rule. Take it more as a guideline of what you should follow close to. Okay? I want to make sure that you have that proper understanding of this aeroponics calculator. I want to encourage you to leave comments about the aeroponics calculator and let me know if I'm going in the right direction. As you know, I try to leave a feedback to all of your comments. Many of you have left comments saying you need to add a conversion for metric. And I agree, we will. I didn't want to add the conversion until the calculator is more stable, until the code base is more stable. Because right now I am making a lot of changes and edits. And if I try to add the metric conversion right now, it will slow down the development of the calculator. So please be patient with me. Eventually, it will have a metric conversion. A beauty of this calculator, of the Aeroponics calculator, is that you would know how your system will perform before it is even built. And that's one of my goals, is that this calculator will achieve that. This tool, the Aeroponics calculator, will save you a lot of time. Currently, I keep a logbook of my designs where I try out different parameters and ranges to see if the system will function the way I want it to. With this calculator, a lot of those steps will be automated. So even for me to design a system, or if someone asks me a question, I no longer need to go through and write it down and figure it out. I can push the numbers through this calculator to give them the answer that they want. This tool is not only beneficial for you, it be also used by me. So let me go through and review this tool. Well, how can this tool be used? Let's say that you're designing a high pressure aeroponic system, but this will also work for any type of aeroponic system. It will save you from redesigning something that you tried or experimented with or built. So this tool will help you to save money. And what do I mean? Well, this will help you to design your system to use the components that are needed, not just because you speculate that you might need something bigger, more powerful, like tubing size. Do you really need to go to a 1/2 inch? Pump. Do you need to use a pump that draws 3 amps? Or can you function properly with the pump that draws 1.5 amps? Backup power, the UPS. Do you need to have one that is a 300 amp hour? Or maybe a 60 amp hour? Or maybe you need a 40 amp hour source. What about the pressure tank? What size of pressure tank do you need? Do you need to have a 1/2 gallon pressure tank? Can you function okay with a gallon pressure tank? Or do you need actually a 5-gallon pressure tank? I mean, the bigger the tanks, sometimes the cost does not go up incrementally. It goes up at multiple prices. Sometimes when you use components that are smaller than the national average, or sometimes when you use components that are larger than the national average, the cost can be quadruple, 10 times, even 20 times. So this tool will help you to determine if you actually need to downsize or you actually need to upsize from the standard. And this will help you save a lot of money. Another thing this tool will help you is save time. Time is money, time is energy. You might be busy running other businesses. You might have other obligations. So this tool will help you design your system right the first time and give you more time to spend elsewhere. Okay, so now let me give you an update of the Aeroponics calculator. First, let's go back to the misting system which we reviewed last time. I added 2 new parameters to this form, and that is the nozzle working pressure. Because as you know, is that as I evaluated the nozzles that I'm using, when I evaluated the nozzles that I'm using, I discovered that that nozzle still performs pretty well at around 60 psi. At 60 psi, it delivered 50 microns or droplet sizes. It delivered a size of 50 microns in droplet sizes or even smaller. So we know that it can function down to 60. But normally when I design my system, I design it to operate at 100 psi. So what ranges would I put in here? I would use some type of safety margin. So I would put in a range of between 100 and 70 or 70 psi to 100, so that we're not quite running it all the way down to 60. We got a little bit of buffer room in there for some type of errors. But so here I'm going to use a range between 70 and 100 psi for the working pressure of my nozzles. Okay, and then I'll put in 100. Okay, for the maximum. So this would be the range of the nozzles. Now the flow rate of the nozzles that I'm using is 0.02 gallons a minute. Okay, we could put in a little bit more to get a little more buffer room. We say 0.0. Let's put in 0.04. How's that? Okay, gallons per minute for our nozzles. Now for here, let's say that we are running 5 nozzles. So we're running 5 nozzles. Okay, so let's say that we are running 5 nozzles. So you put in 5 nozzles. Now I want you to look at this value here for the delivery flow. The delivery flow right now for these 5 nozzles will be 0.1 gallons per minute, which makes sense. If you're running 0.02 gallons per a nozzle, and then so I want you to pay attention to this value here where I have 0.2 gallons per a minute, which makes sense. If each nozzle is demanding 0.04 gallons per minute and we have 5 of them, that times 5 would equal 0.2 gallons per minute. Now this value for the delivery flow has to be also shared on the delivery system. So the missing system values are also shared on other forms. So this number you will see also on the delivery form. So let's go to the delivery system. Okay, and if you look down here where it says delivery flow, that number is just copied over from the missing system. Okay, let me go ahead and clear these so you don't confuse you. Okay, and so I want you to pay attention to the nozzle pressure. Okay, so it makes sense that if we don't have any nozzle, it makes sense that if we don't have any fittings or tubing, there's no loss in the system, right? Because there's nothing to cause this value to go lower because of the transmission of our nutrient. So I want you to watch this value, 100 psi, as we add components into this form. Okay, so the first thing, let's put in the inside diameter of our tubing. Okay, so that's the first thing that we want to look at is the tubing properties. So the first thing we want to put in is the tubing specifications. So we want the inside diameter. So the inside diameter of normally of a 1/4 inch tubing of 0.25 is around probably 0.18, give or take a little bit more. Okay, so we put in 0.18 inches for the inside diameter of the tubing. The next value, we need to know the length of our tubing. Well, what value will we use? Because we know that our tubing from our tank to our nozzle, it varies, depends on which growth chamber you're referring to. We want to use the worst case scenario. The worst case scenario would be chamber number 1 because it's the furthest from our pressure tank. So the distance from the pressure tank to this 90 is 5 feet. Then we need to know the horizontal distance, which is from here to here, which is, we'll say, is another 3 feet. So that means the total distance to the furthest nozzle on growth chamber number 1, which would be the worst case scenario, would be 8 feet. Okay, so, but remember, this field wants the value in inches. So we need it times 8 times 12, which equals 96 inches. So we'll enter 96 inches. And notice what will happen to this nozzle pressure value. Okay, so I'll put in 96. Okay. So I put in 96, and notice what happened. What happened is that our nozzle pressure lost roughly about 1 psi due to the length of tubing that we have in the system. So 8 feet of tubing would cause about a 1 psi drop at your nozzles. Okay, so this is stuff that you need to know. And so this field here tells you the total loss due to your tubing. Okay, the next thing we need to put in is the height above the tank. So when we were saying that the height, we need to know the worst case scenario. You basically have 3 different heights. The worst height is chamber number 1. We already mentioned that the distance from the tank to this 90 was 5 feet. So that's what we would use for a height. Once again, we want it in inches. So we'll put in 60 inches for the height. Notice that our pressure at our nozzles dropped again. Now we're down at 97. Okay, so we have a loss of about 3 psi due to the height of our tubing. Okay, so you look here, you say, well, what was the loss due to the height? Well, due to the height, we lost about 2.2 psi of pressure. Okay, now let's move on. Now we need to know how many fittings we have. Once again, we want the worst case scenario. And when it comes to T's, there are actually two different flows through a T. You have the through flow, which is this direction, and then you have the branch flow, which is this direction. So right now, the calculation does not distinguish the difference between the branch and the through flow. Okay, but the through flow is always going to be less than your branch flow. We'll add that later into a calculator. So in this scenario, we have 2 T's, right? And we have 190 at the end. And that's the number of fittings we have. So basically all you have is 2 T's and 190. So in our calculator, in this field here, we got to put in the number of T's. We got 2 T's, so I put in 2 T's. And then in this field here, we put in the number of 90s. We have 190. Okay, so now if you look at our nozzle pressure, basically this is our nozzle pressure at the worst case scenario for this nozzle right here. Okay, it's receiving 96 psi when the tank is delivering 100 psi. So that's the loss. So we look at our total fitting loss is 0.74 psi. Okay, due to the fittings. Okay, so another thing we have here is that we have a solenoid. Okay, that's one of the components in this system. So it's not really a fitting, it's a component. It's actually an active component. Okay, so down in our components, we have a count for solenoids. So we'll add 1 solenoid. Okay, so that 1 solenoid is causing a drop of roughly about another 1 psi. Okay, so now we can get our total psi loss. Okay, by going back to the top here. So this is our total psi loss, roughly about 4.6 or about 5 psi. That means that our nozzle pressure, that will be the worst case scenario, will be around 95 psi to this system. Now, let's say that, okay, we're trying to run more nozzles into the system. So we go back to the misting. Okay, and let's say we want to run this just for argument's sake. We say that we're trying to run 50. We're trying to run 50 nozzles. That means now we got 5 gallons per minute. So let's go back to our delivery system. Okay, so when we go back to our delivery system, you can see that our gallons per minute has actually increased to 2 gallons per a minute. So now if I actually increase it by 10 times, that means that I try to run 50 nozzles. Will the system still work? Okay, so we go back to our delivery page. So now we go back to our delivery system page and look at the results. It's not looking good. We actually got into the negative pressure when it comes to a nozzle. You get unexplained behavior on your system. Basically, you're not going to know what's going to happen. It's going to be a hit and miss. This is called a hit and miss design, meaning that we don't know what type of nozzle performance that we will see in our grow chamber. Okay, so the total loss is basically greater than what our pressure. So the total loss is greater than our delivery pressure. Okay, so this system here, if you try to push it to 50 nozzles, your system will fail eventually if it didn't already out the gate. So you wouldn't go with this design. You will modify this design so that this parameter, okay, is no longer so that this parameter is no lower than 70 psi, which would be dictated as the working pressure for our nozzles. So you can see how this would be very beneficial to the designing of your high pressure aeroponics system. Now, one value that we didn't quite look at, and that is the residence time. So at 2 gallons per minute, okay, how long would it take the nutrient to leave the tank and actually reach the furthest nozzle? Okay, once again, this is the worst case scenario, because we know that the path from here to here is shorter than the path from here to chamber number 1. So here we're talking about the residence time for the longest path. Like, how long will it take a nutrient if it started here to end up at this nozzle? Okay, so at 2 gallons per minute, okay, the residence time will be roughly 1.27 seconds. So it will take a little over 1 second for the nutrient to reach the nozzle at the time of entry, or at the time of exit. So at the time of exit from the pressure tank, it would take roughly a little over 1 second to reach the nozzle, the furthest nozzle on chamber number 3. Later on, we will discuss why the residence time is critical when it comes to the designing of your high pressure aeroponics system. So I hope that is helpful, that you're able to see the form. Now let's look a little bit at the bottom here at the components. Okay, so this is obvious, you know, if you have any 95 degrees fittings in your system, this would go here, or you might have any couplers in your system. Another thing that you can do is add like any valves. If you have any valves, you will also add that in this component count. If you have any filters in the system, which I recommend, you would add that also to the component count. And if you have any check valves, that's another thing too that you need to add to the system. Now, as I mentioned before, you should never install a check valve between your pressure tank and your nozzles, because it will cause a major performance hit to your system. Okay, so hopefully that gives you enough of review so that you're now updated to where I am with the aeroponics calculator. Now the last form to complete is the charging form, which is a more simpler form because basically it includes the pressure tank and your pump. And that's where we get to the area of power consumption. What I mean is electricity, which will be used to determine the pump that you should buy for your system, as well as the power usage that your system will be using. Okay, and then after we finish the charging system, we will start to develop reports. Now the report is another area that, as I mentioned at the beginning of this video, will entail a lot of my personal design. So when you use this aeroponics calculator, in a sense, you're really getting my advice on your design to make sure that it will fit Lee's criteria to a professional aeroponics system design. And as I said before, please leave comments below if you have suggestions to make about this aeroponics calculator. If you want to thank me, the best way you can do that is by clicking on the like, thumbs up button below. I look forward to talking to you in the next video as we take your garden into the future.